Okay, so I won't keep you long today, but I want to finish up a couple of application problems, and then we'll start with geometry starting Friday. So although we started off writing the geodesic equation, we never used it. Alpha beta dx alpha tau. This is for time like. If it's this is for time like geodesic. For a light like geodesic, we'll talk more about that. It'll satisfy the same looking equation, but the parameter tau might have a different meaning. So we, in fact, won't use tau. What would be the problem with tau in time like? So if you recall, and please, it's this, right? Where in this notation, x dot mu, that's dx mu, some parameter ds, and this is going from maybe 0 to tau. Oh, 0 to some s. And you get a function of tau. Tau is a function of s. And then you get rid of the function s and you write it as a function of tau. But we can't do this for null geodesic, because for null, this is 0. So it is just some arbitrary parameter for a null geodesic. But again, I'm talking about timeline for the moment. Okay? But we cheated. We said this equation can be derived by defining this to be the Lagrangian. And which by Lagrangian, you minimize an action and you get a Lagrange equation. They're called Euler equations of motion. dl dx dot mu minus dl dx mu equals 0. And when we did this, there are two constants that emerge. It emerges due to the fact that Ct is equal to 0, because there's no time dependence here. And this led to the conservation of energy. And in exactly the same way, conservation of angular momentum. I must clarify, when I was talking about Lagrangian, I thought all of you had seen Lagrangian formalism. In the Lagrangian formalism, you have, let me be very explicit, it consists of 8 variables: x0, x1, well, minus 1, x2, x3, and also x dot 0, x dot 1, x dot 2, x dot 3. So there are 8 of them. They're considered to be independent variables. And that's how you would get Lagrange's equation of motion. So we have 2 conserved quantities here. We have a third conserved quantity, which is what? Which is, well, L equals G mu nu x dot mu x dot nu. Remember, this is nothing more than G u u, which again for time-like particles is minus c squared.
3 vector or 4 vector?
4 vector.
4 vector.
Yeah, but you know, it's 0, 1, 2, 3, so 4. So there are 4 unknown coordinates, right? x0, x1, x2, x3. There are 4 of them, but there are 3 conserved quantities. Therefore, the equations can be really trimmed down, and you can get an equation with just one variable to solve. This is why we're able to actually solve things. by not actually writing this differential equation. So you can also see this Lagrange's technique makes things a lot easier. It identifies constants of motion, and then it'll help you solve equations a lot faster, a lot cleaner, not faster in terms of time, but in terms of idea. And then when you do that, so out of the 4, you have 3 constants, so therefore you'll only have 1 variable, and the geodesic equation boils down to in the homework you'll verify this 2mr squared minus gmm over r equals m over 2 kappa squared minus c squared. And r dot, of course, is dr d tau. Now this is with the understanding that theta dot is equal to 0. As a matter of fact, we picked theta to be in the equatorial plane, because when you have a perfect sphere, there's no preferred equator, but any geodesic motion will be restricted to an equatorial plane. And to justify that, in your homework, I have asked you to show that theta equals constant satisfies the theta geodesic equation. Okay? It just saves you a lot of trouble. All right, so basically what's happening is T dot is being replaced by epsilon, phi dot is being replaced by L. So then you only have, when theta dot is 0, you only have an equation in R dot. Okay, these are simple, but I've left a lot of this details for you to verify in your homework, and you must do so. And when you do that, and I think I even started this, what I did was R dot, I wrote it as dr d phi d tau, and this is dr d phi, and d phi d tau is nothing but L over mr squared. I recall Jackson saying, where's the sine squared theta? But it's in the equator, so sine squared theta is 1. And from this, and so now I have this on one side, which is equal to R dot, and I can stick it back in here. And for our purposes, so what we're going to do, I want to clarify what we're doing, because in the next 2 problems that we're doing, 2 experimental verifications, you will verify all the details as homework, but I want you to understand the plot, and you're just verifying an integral. At the end of the day, that's all you're doing. Okay. So the first problem we're doing is the perihelion advance of Mercury, and that is when a geodesic rotates, it comes back by 2 pi, it goes a little further than, one orbit, it just changes the angle. So to clarify that, from this equation, in putting this in, I can get d phi, or d equals square root of a over r squared, a over j squared, I want you to verify all of this, minus 1 over 2 dr, and I also want to tell you what they are. I'm not sure if I did give it, but I want to state it one more time, because we're just clarifying all the details. Yeah. So the A is nothing but 1 minus 1 over 1 minus r star over r. J is related to angular momentum. And E is related to the energy. It's inverse energy, so to speak. Now you might say, well, what is it we're calculating? Well, there is an R, let me make it like this, let me exaggerate it. There is a R minus, which is the smallest value of R, and there is an R plus, which is the largest value of R. And so, oh, I did this last time, I did it again. So now what I'm going to do is I'm going to go from R minus to R plus, from here to here, and then multiply that by 2. Yeah? You will find that this angle is greater than 2 pi. So the perihelion advance is simply, and if I call this delta phi, perihelion advance is nothing more than delta phi minus 2 pi. Normally, we would, for Newtonian physics, it would be 2 pi. But in relativity, it would be more than 2 pi. And I'm not sure if I presented the numerical value and the numerical calculations. I also want to say something. When you look at this, when you try to integrate all of this, there will be it is impossible to integrate this exactly. So what you want to do is find the smallest change from 2 pi, the lowest order. Now, I talked about this early. There is a parameter which is very small in all of this. What is that parameter? One thing that is all over here is what?
R star.
R star over R for the sun. So for the sun, this is
10 to the 6.
10 to the minus
10 to the minus 6.
6. So R star, 2gm over c squared, g is 10 to the minus what? I can't recall at the moment, but it's a very, very small number. R star is very small. So we will calculate this, or rather, you will calculate this. I've given you problems step by step. You just carry out one after the other for the lowest order term in R star. Now, how do you approximate things to the lowest order? I just want to clarify this. But before we do so, it turns out perihelion advance is going to be 2 times phi at R plus minus phi at R minus 2 pi. And that, to the lowest order, is going to be 3gm over c squared. I'll give you hints on how to calculate radians per revolution. I got these numerical factors directly from Weinberg's textbook. The value for this, for Mercury, is 3.6166 times 10 to the minus 8, 1 over kilometers. Gm over c squared, big M, so the mass of the sun, over c squared. We need that because that's over here. And that is 1.475 kilometers. And so the perihelion advance is going to be, the advance is going to be 3 times 1.475 times pi times 36166 10 to the minus 8 radians per revolution, putting all these numbers in. Where did I get 1 point? Yeah, there it is. Yeah. It's going to be this, and this is 5 times 10 to the minus 7 radians per revolution. This doesn't mean anything directly to us, but this is too small a number, so you would convert this to arc seconds, and I would get 0.103 arc second per revolution. And Mercury, I've mentioned this before, Mercury makes 450 revolutions in a century. And therefore, the advance, when written, and we don't have to worry about all these numbers, but you should calculate and make sure that the math is right. You will find the advance to be equal to 415 times 0.103, which is 43 arc seconds per century. The answer is not 42, but 43. Okay, now how do we get from here to here? There are 2 steps involved. One is a coordinate change, and the other is the approximation. Coordinate change is easy. Coordinate change is given to you, you substitute, the integral becomes doable. But there is an approximation, smallest value of r. So when you do this integral, by the way, this is the result. So when Mercury goes from the shortest distance to the longest distance and comes back to the shortest distance, it has gone a little past 2 pi. That's when it gets closer, right? So that has been measured. 43 arc seconds per century. It's an incredible feat. And as someone who spends more time with theory, I couldn't even imagine how one thinks of an experiment like this. One by one, many of the results have been experimentally verified. Quantum mechanics has been verified to great precision. These are all incredible feats. I think the recent Nobel Prize was given in physics for measuring the macroscopic effect of quantum tunneling, as you heard from the talk recently, right? Easy to say these words, but how do you measure it? You know? Okay, so one of the quantities you will encounter in simplifying, I will expand it for you, is this one. And I'm using the same notation I've used in the homework in building up the calculation, is quantity c to the minus 1/2. That is simply 1 minus r star over r minus 1 over r plus. Okay? Temporarily, just temporarily, I'm going to call this alpha. So it is 1 over square root of 1 minus r star alpha. So when I say approximate this to first order, I will calculate this at r star equal to 0, Taylor expansion. Plus, I will take the derivative with respect to r star and then evaluate it at r star equal to 0, and then, so this is a number times r star. Then I might have r star squared, cube, so on and so forth. This is the process of doing it. So let's do it for this guy so that there's only one other term that you'll be doing it for, and it's a similar term. So when I put r star equals 0, I get 1 over 1, which is just 1. So this is the 0th order term. This will, give you the Newtonian answer. Plus, there's a correction. Help me take the derivative. What is the derivative of 1 over square root of 1 minus r star alpha?
1 over.
So that is minus 1/2 becomes a 3/2, right? This will become 1 minus
R star cube. Oh yeah, 1 minus R star alpha cube.
r star alpha
Cube
to
square root
the
2.
3/2. Then what do I need to do? Oh, then do I multiply by 2/3?
No, not yet.
No,
First
by
one.
1/2. It's minus 1/2.
Yeah.
Minus 1/2.
But then it's already negative on the inside, so you make it positive.
And then I have a negative
Alpha.
alpha. So when I get the answer, what do I do? R star alpha, and then evaluate it at r star equals 0. I simply get
Negative 1 over 2 or negative positive alpha.
yeah. So when I approximate this, I should really have not written equal to. That's how I approximate it. The 0th order term and the 1st order term. Sometimes, and just to make life easier, you may have to multiply 2 terms. So when you multiply 2 terms, you will get a constant term, you'll get an r star term, then you'll get an r star squared term. Once again, you ignore the squared term. Because r star is so small, you're willing to just hang on to the first factor. And this is how you would calculate the
And you
integration. Huh?
keep the R star on the outside down.
Oh, sorry. Yeah, thank you. This is the 0th order term, this is the 1st order term. And then the homework will guide you towards the expression that I wrote over here. We'll do one more experimental calculation. This too is just a calculation that is mostly relegated to the homework, but I want to set it up, explain the physics of it, and what has been measured. So this is the Shapiro time delay. Oh. So you have a beam of light. Here is, say, Venus, and this is Earth, and here is the sun. And I'm going to erase this, so don't write this down. If you send a beam like this, because of the sun's gravitational field, you'll see, null geodesics will do this, it'll go this way, and it'll miss Venus, right? Because space and time itself is bent, and light goes in a straight path in a curved space-time. So the one that makes it to Venus is one that goes this way. I mean, as it goes this way, it gets bent, so and you have to precisely match it so that it hits correctly. Now, if the sun didn't exist, well, we won't exist. Let me rephrase that. If we send a beam of light to Venus and measure the time taken for it to come back, when the sun is not in between. When that happens, this will be perhaps the path that's taken. Obviously, this path doesn't require as much time as it would require with this one. This will be the 0th order term. This will be the first order term. Okay? So, a little bit of notation while I set it up. This distance, closest distance, is called R0. This is RA for the first object. So, you can think of A, B. And this is RB. These are the parameters that will play into this. But this time, we're sending a beam of light so we need a null geodesic. A null geodesic indeed satisfies the geodesic equation. Let me just be pedantic here and write this carefully. It'll exactly look like this, but I don't have a d tau. So I could use an S or lambda. I don't want you to be obsessed with the parameters, so I'm going to just make a change and call it lambda here. Gamma mu alpha beta dx alpha d lambda dx beta d lambda equal to 0. Once again, this is given by a Lagrangian. Same Lagrangian. So you can expect its energy and its angular momentum of the photon is conserved. And on the other hand, G mu nu, sometimes I write, let me just do it this way. Is equal to this. And so, instead of minus c squared, I would have 0. The equation is the same. R star over R, c squared dt d lambda squared, plus 1n for the R component. This is in the denominator, so I put it as minus 1, dr d lambda squared, plus r squared d theta d lambda squared plus r squared sine squared theta d phi d lambda squared. This is the null geodesic equation. I want to clarify a little bit of notational changes, because when we defined energy and angular momentum, previously we had an m. We just threw it in there because far enough away it becomes mc squared gamma. We don't have an m. So let's not throw in there. So very specifically, I'm going to call, and this will be the conserved quantity kappa, but it has a different definition. There's no m there. C times, let me call it T lambda, where T lambda is dt, T prime, which is dt d lambda. Okay? So because it's not proper time, I'm not using dot, I'm just using lambda. And angular momentum, J, is r squared sine squared theta phi lambda. Once again, I'm going to take this, put these constants in, and set theta equals what? Pi over 2. So I will get a very simple equation. This is minus r star over r, c squared t prime squared, plus 1 minus r star over r, inverse r prime squared, plus r squared phi prime squared. T prime is related to kappa, phi prime is related to J, and therefore I'll only have an equation at R, and I would get R prime squared equals kappa squared minus J squared over R squared A, where A is as before. This is very simple equation. And we'll have occasion to solve this exactly eventually. This will become important. We'll be exploiting the properties of space and time, studying null geodesics. So I'll actually integrate this for you. But today that's not the goal. So I can write, I'm setting up the problem. So right over there, dr d lambda, we'll just take a square root and bring out convenient factors. As I take a square root, there's a plus or minus, and this j, this makes it easier for analysis, b squared minus 1 over r squared, 1 minus r star over r to the 1/2 here b is j over kappa. And what I'm interested in is the time taken, c dt, well, c delta t equals integral of c dt equals dt over dr dr. And simplify this, dt over dr equals dt over d lambda, because I can relate it to this, times d lambda over dr, which I can get by flipping this. Okay? When you do all of this, again, there's a 0th order and 1st order approximation. I would like for you to follow through. With the calculations, and your homework will take you there. I can write dt to be equal to dt0 plus. What do you think dt0 is? As of the straight path, plus the delay. And turns out, c dt, as you will verify in your homework, is RA RB over R0 squared. And that happens to be about 200 microseconds. Oh, so obviously that is so Shapiro predicts a 200 microsecond delay, and that has been verified. So I know this is an unusual lecture. I don't think I know I won't do this again. I just told you the plot of two problems so that when you look at these problems, you know why you're doing all of this. And these are very important tests of the Einstein equation, or equivalently, the fact that the Schwarzschild geometry describes the gravitational field of a round object. a spherically symmetric object.
So is this saying that because light is traveling so fast that it's only 200 microseconds? Or
No. This is the little delta t.
so this is literally just the difference in the path?
Yeah, it takes more, because the sun is in between, it takes more time.
So in this case,
Yes,
is the arc just extremely slight?
extremely.
Oh,
Yeah.
Because I was thinking like, I was
Yeah.
200
If
microseconds is
listen,
nothing.
if I drew it, it'll look exactly like that.
Okay, yeah.
Yeah, so I'm
it's
to exaggerate,
very
yeah.
small.
This is a massive sun. In Krypton, I don't know how massive Krypton is, but
Blue.
we assume it's more massive. Yeah.
Right.
So because of the curved path, even my, precession has been exaggerated. Remember, it's
Yeah.
43 arc seconds per century. So that's what you get. If you have any questions along the way, please ask. It is not difficult conceptually, but gosh, you just have to go through those integrals. It's not difficult to do. You just have to be patient till all the expressions in between are given to you. So you're just verifying each problem. The problem says show this, and it says show that, right? So just connect the dots, and you'll get the answer at the end.
Is this not based off of the angle that the sun makes between the two planets?
Yes, but that is captured in the fact that we know RA, R0, and RB.
Oh, okay.
Yeah.
But so for a specific RA, RB, and R0,
Correct.
200 microseconds.
Correct. Yes.
Because
Very good.
that will change if RA, RB, or R0 changes, correct?
Correct.
Yeah.
And I'm trying to think if I have mentioned that along the way. I may not. So I will look up Weinberg's book, but you should too. You guys should. So if you were to keep a book on gravity, and if you're not going to be interested necessarily in general relativity and its theoretical formulation, Steven Weinberg's Impenetrable book is a great book to have. He does physics. He says right in the beginning, I'm not here to describe the geometrical theory of gravity. I'm here to describe general relativity and its measurement. He talks about cosmology. It's a great book. It's a readable book. It's very thorough. The math is old-fashioned. It uses things that we are comfortable at the undergraduate level. He just uses quite a bit of it. Yeah, but he describes everything. I'm not saying it's an easy book to read, although it doesn't have any really new techniques per se. But I think with this course, it is a good book to read, and it's a great companion. Yeah, so consider buying the book, but at least go to the library and look up the details of what R0, and I look up the same as well. But again, this is very uncharacteristic. End of the semester, here I am just describing a problem to you, and you'll verify it at home. Starting Friday, it's back to normal lectures. We'll be probing the geometry of Schwarzschild spacetime. We will in fact go to show that this metric as it is written is not the best way of writing the metric if you want to poke your finger into R equals 2m. Right now, you can't because there's an infinity there. And many years, I think he passed away recently, but there was a dude walking around Georgia Tech. His name was Finkelstein. So Finkelstein, along with the famous astrophysicist Eddington, constructed a new coordinate system where the singularity disappeared at the event horizon, so-called event horizon, which means we're able to probe it. We will construct it intuitively. We probe geometry with geometric objects. We will send light signals. Light has always been the wild card for us. We'll send light signals to understand what happens when you reach R equals 2n. And then you realize, well, it's not so bad at that point. Maybe later on you might have a problem, but there you're okay. But you'll also realize, whoa, what's going to happen next depends on how you set up the coordinate system. There's one coordinate system where you're ill-fated. There's another coordinate system where you're kicked out. It's the white hole. Yeah? So as it is, the Schwarzschild spacetime written by Schwarzschild coordinate system is just entry, and this is the first solution that was found, but it's just entry into the problem. So we'll construct what's called the maximal Schwarzschild geometry. Now all of it, in all its generality, don't have to exist in this universe. But if they do, it's a pretty drastic picture from what you and I are familiar with. And we'll explore it in all possible detail. Yeah? And that I can easily do this semester, and that's how we did it this semester.